Welcome to today's session. In this video, we will explore LeetCode problem number 396, titled Rotate Function. This problem challenges us to work with array rotations and optimize the computation of a mathematical function. Let's dive in to understand the problem and its solution approaches. In this problem, you're given an integer array nums of length n. What's unique about this array is that it behaves like a circular array, meaning that the element after the last one, nums, and 1, is the first element, nums, 0. Similarly, the element before the first one, nums, 0, is the last element, nums, and 1. Based on this, we define something called a rotation function, f, k. Here, k represents the starting index of the rotation, and the function calculates a weighted sum where each element in the rotated array is multiplied by its index. The formula for f, k, is 0 asterisk nums, k, plus 1 asterisk nums, k plus 1, %n, plus 2 asterisk nums, k plus 2, %n, plus n1 asterisk nums, k plus n1, %n. Your task is to determine the maximum value of f, k, across all possible rotations, where k ranges from 0 to n1. Let's take a look at some examples to understand this better. For the input nums equals 4, 3, 2, 6, we need to calculate f, k, for all possible values of k. For k equals 0, the rotation function evaluates to 0 asterisk 4 plus 1 by 3 plus 2 by 2 plus 3 asterisk 6, which simplifies to 0 plus 3 plus 4 plus 18, resulting in 25. For k equals 1, the function is 0 asterisk 3 plus 1 by 2 plus 2 by 6 plus 3 asterisk 4, giving us 0 plus 2 plus 12, which equals 26. Similarly, for k equals 2, the result is 23, and for k equals 3, it's 16. Among these, the maximum value is 26, so that is the output. In another example, where nums equals 100, there is only one element, so regardless of the rotation, f, k, is 0. This is because all terms in the formula are multiplied by their index, and the only index here is 0. Now let's consider the constraints and edge cases. The length of the array, n, can go up to 10⁻⁵, so your solution must be efficient and avoid recalculating f, k, from scratch for each rotation. The values in the array can range from -10⁻⁹ to 10⁻⁹, meaning that the function needs to handle large positive and negative numbers. Some notable edge cases include a single element array, where f, k, is always 0 since no rotation changes the result. If all elements are 0, f, k, will also be 0 for all rotations. Finally, when dealing with large inputs, the solution must be optimized to handle the maximum constraints without significant performance issues. To solve the rotate function problem, one intuitive method is the brute force approach. The idea here is to directly calculate the value of the rotation function, f, k, for each possible rotation index k. The formula for f, k, incorporates a weighted sum of the array elements, where each weight corresponds to the index after rotation. Specifically, the formula is f, k, equals 0 asterisk nums, k, plus 1 asterisk nums, k plus 1, plus 2 asterisk nums, k plus 2, and so on, until n1 asterisk nums, k plus n1, with modular arithmetic ensuring the circular nature of the array. This means that as we rotate, the indices wrap back to the start of the array. To implement this, we iterate over all possible rotations, compute f, k, for each one, and track the maximum value. While this approach is straightforward and easy to understand, it requires recalculating the sum of products for each rotation, which leads to a time complexity of n squared. This makes it inefficient for larger arrays. The brute force approach, while conceptually simple, has significant drawbacks due to its inefficiency for large arrays. To optimize it, we can take advantage of a key observation: there's a direct relationship between consecutive values of the rotation function, f, k, and f, k plus 1. Specifically, f, k plus 1, can be derived from f, k, using a formula, f, k plus 1 equals f, k, plus some, nums, and asterisk nums, n1 k. This insight eliminates the need to recompute f, k, from scratch for each rotation. Here, sum, nums, represents the sum of all elements in the array, and n asterisk nums, n1 k, accounts for the impact of the rotation. With this formula, we can iteratively calculate each rotation function more efficiently. To implement this, we start by computing f0 as the initial rotation function value through a single pass over the array. We also pre-compute some nums to avoid redundant calculations. This approach significantly reduces the computational overhead compared to brute force. Once we have f0 and some nums, we can calculate each subsequent f(k) iteratively using the relationship between f(k) and f(k plus 1). While iterating, we continuously track the maximum value of f(k) to determine the result. The optimized approach improves the time complexity dramatically. Computing f0 and some nums both take O(n), and deriving f(k plus 1) from f(k) for all rotations also takes O(n). Therefore, the total time complexity is reduced to O(n), making it suitable for large input sizes. In terms of trade-offs, this approach is far more efficient than brute force and scales well for large arrays. However, it is slightly more complex to implement, as it requires understanding the mathematical relationship between consecutive rotation functions. Despite this, the significant performance gains make it a strong choice for competitive programming scenarios or large datasets. Comparing the two approaches, the brute force method is simple to implement but fails to scale effectively for large arrays due to its O(n)² time complexity. On the other hand, the optimized approach is both efficient and scalable, reducing the time complexity to O(n). While it is slightly more involved to implement, the relationship between consecutive rotation functions makes it manageable with careful planning. Ultimately, the optimized approach is the clear choice for this problem as it balances efficiency and clarity. It allows us to handle the constraints of the problem while avoiding unnecessary computations, making it the most practical solution for real-world and competitive programming scenarios. In this problem, our goal is to calculate the maximum value of a function f(k) for a given array nums, where k represents a rotation of the array. The function f(k) is defined as a weighted sum of the elements of the rotated array, with weights ranging from 0 to n1. The array is treated as circular, meaning that when the indices go beyond the array length, they wrap around to the beginning. To solve this problem efficiently, we need to leverage the properties of the array and the function definition. First, we compute the initial value f(0) using its direct formula, which involves iterating through the array and summing the weighted contributions of each element. This gives us a baseline to build upon for further calculations. After calculating f(0), the next step is to compute the total sum of all elements in the array, denoted as total_sum. This will be a critical component in reducing redundant calculations. Once we have f(0) and total_sum, we establish a recurrence relation to efficiently compute f(k) for any rotation k. The relation is derived as f(k) equals f(k1) plus total_sum n asterisk nums nk. Here, the term nums nk represents the element that is rotated out of the weighted sum due to the shift. Using this relation, we can compute f(k) from f(k1) in constant time for each rotation. Finally, we iterate over all possible rotations, updating f(k) and keeping track of the maximum value encountered. During the iteration process, we maintain a variable to store the maximum value of f(k) seen so far. Once all rotations have been processed, this variable will hold the result. The recurrence relation is the key innovation here, as it optimizes the computation of f(k) from O(n) per rotation to O(1). Treating the array as circular ensures that we can handle the wrapping of indices seamlessly using modular arithmetic. By pre-computing f(0) and total_sum, we avoid redundant calculations and ensure the algorithm runs efficiently. Additionally, this approach uses only a few scalar variables for storage, making it space efficient. Analyzing the complexity, the algorithm runs in O(n) time. Computing f(0) and total_sum each take O(n), and iterating through all rotations involves O(n) updates, with each update being O(1) due to the recurrence relation. The space complexity is O(1), since we only use a few additional variables beyond the input array. For edge cases, if all elements in the array are equal, f(k) will be the same for all k. For a single element array, f(0) is the only value to compute. Finally, the algorithm is well suited for large arrays because it processes the data in linear time, ensuring scalability. To illustrate, let's consider an example with the array nums equals 4, 3, 2, 6. In this example, we start by computing f0 directly as the weighted sum of the elements f0 equals 0 asterisk 4 plus 1 asterisk 3 plus 2 asterisk 2 plus 3 asterisk 6 equals 25. Next, we calculate the total sum of the array, total underscore sum equals 4 plus 3 plus 2 plus 6 equals 15. Using the recurrence relation, we compute f1 as f0 plus total underscore sum n asterisk nums n1 equals 25 plus 15 4 asterisk 6 equals 16. Similarly, f2 is derived as 16 plus 15 4 asterisk 2 equals 21 and f3 as 21 plus 15 4 asterisk 3 equals 24. Among these, the maximum value is 25, which is the solution. This example demonstrates how the recurrence relation simplifies the computation and how we efficiently find the maximum value of f(k). This implementation efficiently calculates the maximum rotation function value for a given array. First, we note that the naive approach, which computes f(k) for all possible rotations explicitly, would be computationally expensive with a time complexity of O(n squared). Instead, we derive an optimized formula for f(k) in terms of f(k1) to achieve a linear time complexity O(n). The key insight is that the rotation function f(k) can be expressed recursively. f(k) equals f(k1) plus total underscore sum n asterisk nums nk. Here, total underscore sum represents the sum of all elements in the array, and nums nk corresponds to the element that gets rotated out during the kth rotation. Explanation of the code. 1. Initialization asterisk. We start by calculating the total sum of the array, total underscore sum, and the initial rotation function value f0. f0 is computed as the weighted sum of the array elements, where each index is multiplied by its corresponding value. 2. Iterative calculation of f(k). Using the recursive formula, we iteratively compute f(k) for each rotation based on the previously computed f(k1). During each update, we determine the maximum value encountered so far. 3. Result asterisk. After iterating through all rotations, the maximum value is returned as the result. Complexity. Time complexity asterisk O(n), since we compute f0 in O(n) and perform O(n) updates for the subsequent rotations. Space complexity asterisk O(1), as we use only a constant amount of additional memory. This optimized solution ensures that the problem is solved efficiently even for larger arrays, adhering to the constraints of the problem. Here, we're diving into the Java implementation of the rotate function problem. First, we start by importing the necessary utilities and defining a solution class with a method maxRotate function. The input is an array of integers called nums. The length of the array is stored in the variable n. To begin solving the problem, we calculate the total sum of all elements in the array using a simple loop. This is stored in the variable total sum. Next, we calculate the initial value of f0, which is the rotation function when no rotations have been applied. This involves summing up the products of each index multiplied by the corresponding element in the array. The result is stored in the variable f_k. This forms the base case for our solution. We then initialize a variable max value to store the maximum value of the rotation function, starting with the value of f0. From here, we proceed to iterate through all possible rotations of the array to compute the rotation function values more efficiently. Using a derived mathematical formula, we update the value of f_k in constant time for each rotation, avoiding the need to recompute the entire sum from scratch. After calculating the updated f_k, we check if it exceeds the current max value, and if so, we update max value accordingly. Finally, once all rotations have been processed and we've determined the maximum value of the rotation function across all possible configurations, we return the max value. This marks the end of our Java implementation. The solution is efficient, as the core of the computation relies on a linear traversal of the array and the mathematical formula for updating f(k), making it an O(n) solution. This ensures that the implementation is both optimal and easy to follow. To begin solving the rotate function problem, we start by initializing some key values. First, calculate the length of the input array nums, which in this case is 4. Next, compute the total sum of all elements in the array, 4 plus 3 plus 2 plus 6, which equals 15. With these, we calculate the initial value of the rotate function, f0. The formula for f0 is straightforward: multiply each element by its index. Specifically, 0 times 4, plus 1 times 3, plus 2 times 2, plus 3 times 6. Adding these together gives us 25. At this point, we set the initial maximum value, max_value, to f0, which is 25. Now, as we iterate through the rotations, we use the formula f_k equals f_k1 plus total_sum minus n times the last rotated element. For the first rotation, f1 becomes 25 plus 15 minus 4 times 6, which evaluates to 16. The maximum value remains unchanged at 25 since it's greater than 16. Moving on to the second rotation, we calculate f2 as 16 plus 15 minus 4 times 2, which results in 23. Again, the maximum value remains 25, as it is still greater than 23. For the third rotation, f3 is calculated using the same formula. Adding 23 plus 15 and subtracting 4 times 3 gives us 26. This time, the maximum value is updated to 26, as it surpasses the previous maximum of 25. With no further rotations, we conclude that the maximum value for this example is 26. Shifting to a new example where the input array is 1, 2, 3, 4, 5, we begin again with initialization. The length of the array, n, is 5, and the total sum of the elements is 1 plus 2 plus 3 plus 4 plus 5, which equals 15. The initial value of f0 is calculated as 0 times 1, plus 1 times 2, plus 2 times 3, plus 3 times 4, plus 4 times 5. This results in 40. We set max_value to this initial value of 40 as we prepare for the rotations. Starting the rotations, the first rotation gives us f1 as 40 plus 15 minus 5 times 5. This evaluates to 30, but the maximum value remains 40 since it is greater than 30. For the second rotation, f2 becomes 30 plus 15 minus 5 times 4, which equals 25. Again, the maximum value stays at 40. In the third rotation, f3 is 25 plus 15 minus 5 times 3, which again results in 25. The maximum value is still 40, as none of the calculated values have surpassed it. In the fourth rotation, f4 is calculated as 25 plus 15 minus 5 times 2, which evaluates to 30. Though f4 is higher than some earlier values, the maximum value remains at 40. With all rotations completed, the maximum value of the rotate function for this example is 40. Finally, looking at the simplest case where the input array contains just one element, 100, the initialization step is straightforward. The length of the array, n, is 1, and the total sum of elements is simply 100. Calculating f0 involves multiplying the single element, 100, by its index, 0. This results in f0 being 0. Since there's only one element, no rotations are possible, and we set the maximum value to f0, which is 0. For an array of length 1, there are no additional rotations to compute. The single value of the rotate function, f0, is the final result. Therefore, the maximum value of the rotate function in this case is 0. This example highlights that when the array length is 1, the solution is immediate and requires no iteration. With this, we've covered 3 examples of varying complexity to demonstrate how the rotate function problem can be approached systematically. The time complexity analysis for this problem begins with understanding the initialization steps. First, calculating the length of the array, which is a simple operation, takes constant time or O1. Next, finding the total sum of the array elements requires iterating through the entire array, which takes linear time or O(n). Similarly, the initial computation of f0, which involves summing up the products of each index and its corresponding array element, also runs in linear time since it involves a single loop. After these preparatory steps, the algorithm proceeds to iterate through the rotations. For each rotation, the formula to compute f(k) from f(k1) requires just a few arithmetic operations, making each iteration constant time, or O1. The loop executes for n1 rotations, resulting in an overall loop time complexity of O(n). Additionally, the comparison and update of the maximum value for each rotation are also constant time operations, contributing minimally to the complexity of the loop. Now, combining all the components, the overall time complexity of the algorithm becomes clear. The initialization steps collectively require O(n) time O1 for determining the array length, O(n) for finding the total sum, and another O(n) for calculating F0. The iteration through the rotations adds another O(n), as each of the n1 iterations involves constant time calculations. Summing these contributions, the total time complexity is O(n) from initialization plus O(n) from the loop, which simplifies to O(n). This demonstrates that the algorithm operates efficiently, scaling linearly with the size of the input array. Looking at space complexity, the analysis is straightforward. The algorithm primarily relies on scalar variables and does not require additional data structures. The input array is provided as part of the problem and does not contribute to extra space usage. Variables such as n, total_sum, f_k, and max_value each take up constant space, or O1, as they are simple scalars. Since there are no additional data structures like lists, dictionaries, or matrices being used, the algorithm operates entirely within O1 space. This minimal memory footprint is another key strength of the optimized approach. When comparing the optimized approach to a brute force solution, the efficiency becomes even more evident. A naive method for solving the problem would recalculate f(k) from scratch for each rotation. This involves explicitly generating every rotated version of the array, which takes O(n) time per rotation, followed by calculating the sum by multiplied by the elements of the rotated array, another O(n) operation. With n total rotations, the brute force solution has a time complexity of O(n) for rotations multiplied by O(n) for some calculations, resulting in O(n squared). In contrast, the optimized approach avoids recalculating rotations altogether by using a derived formula to compute f(k) in constant time from f(k1). This reduces the time complexity dramatically to O(n). What's more, the optimized method consistently achieves O(n) time in the best, average, and worst cases since it processes the array in a single linear pass and does not depend on the specific values within the input array. In conclusion, the optimized solution offers a clear advantage over the brute force method, both in terms of time and space complexity. The optimized approach achieves O(n) time complexity and O(1) space complexity, making it highly efficient and scalable for large inputs. In contrast, the brute force method is significantly less efficient, with an O(n squared time complexity and the same O(1) space usage. By reducing the time complexity by a factor of n, the optimized approach underscores the importance of leveraging mathematical insights and formula derivations to streamline computational processes. This efficiency makes it the preferred choice for solving the rotate function problem. When working on the rotate function problem, several common mistakes can trip you up. First, misunderstanding the rotation function formula is a frequent issue. The function f(k) isn't just about rotating the array, it involves recalculating a weighted sum for each rotation. Failing to recognize this distinction can lead to incorrect logic and inefficiencies. Another critical error is relying on a brute force approach that uses nested loops to calculate f(k) for every rotation. This results in an O(n squared) solution, which is not viable for large inputs. Instead, you should aim for an optimized iterative approach that reduces the complexity. Additionally, index handling during rotations often poses challenges. Without properly wrapping indices using modulus, you may encounter out-of-bound errors or inaccurate results. Edge cases are equally important. Make sure to account for scenarios like empty arrays, single-element arrays, or arrays with identical elements. Finally, as you compute f(k), don't forget to dynamically update the maximum value. Neglecting this can lead to missing the optimal solution, even if your calculations are otherwise correct. Now let's dive into some critical insights for interviews. A key takeaway is that brute force isn't just about solving the problem, it's a stepping stone to deeply understanding the structure of the rotation function. This understanding is what helps you derive an optimized approach that avoids redundant calculations. One important pattern to recognize is the relationship between successive values of f(k). Specifically, f(k plus 1) can be calculated from f(k k, using the total sum of the array and the last element of the previous rotation. Leveraging this relationship allows you to compute results iteratively in O, n. During interviews, it's important to articulate the trade-offs between the simplicity of brute force and the efficiency of optimized solutions. Explain why the O, n approach is critical for handling large datasets. Additionally, be prepared for follow-up questions. These might include variations like adapting the solution for circular arrays or modifying the formula. Demonstrating your ability to analyze and extend the problem will impress interviewers. To build a broader understanding, it's helpful to look at related problems. The rotate function itself, LeetCode 396, is the most directly relevant, as it focuses on optimizing the computation of f, k. Another problem to consider is LeetCode 53, maximum subarray. It shares the theme of deriving optimal values efficiently using mathematical relationships. Similarly, LeetCode 238, product of array except self, involves optimization principles but applies them to cumulative products instead of sums. Lastly, LeetCode 189, rotate array, is worth noting. While it deals with array rotations, its focus is on the rotation process rather than a weighted sum like f, k. In terms of alternative approaches, brute force is the most straightforward. It calculates f, k, for all rotations by iterating through the array, but as we discussed, it's inefficient with a complexity of O, n squared. The optimized iterative approach is much better. By pre-computing the sum of the array and the initial value f, 0, you can use the relationship f, k plus 1 equals f, k, plus sum, nums, n asterisk nums, n k, to compute subsequent values in O, 1, per rotation, leading to an overall complexity of O, n. Another strategy involves prefix and suffix sums, though it's less intuitive for this problem and may add unnecessary complexity. Finally, let's compare the trade-offs of the approaches we've discussed. Brute force is easy to implement, making it a good starting point for understanding the problem. However, it's not scalable due to its O, n squared, complexity. The optimized iterative approach, on the other hand, is highly efficient with O, n, complexity, but it requires a deeper understanding of the mathematical relationships in the rotation function. This added complexity might make it harder to implement initially, but the performance benefits are significant for large inputs. Lastly, prefix and suffix sums, while useful in many array-based problems, aren't the best fit here. They tend to overcomplicate the solution without offering substantial advantages for this particular problem. Understanding these trade-offs helps you choose the right approach based on the problem constraints and the context, such as an interview or real-world application. Thank you for joining me today. We reviewed the rotate function problem, explored its brute force solution, and discussed optimization strategies. Remember, mastering such problems strengthens both your algorithmic thinking and coding skills. Stay curious, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!